So far, we've looked at one-dimensional motion. Those are the big four kinematic equations. And we've also looked at vectors, at least in terms of one vector, which has a length called magnitude and a direction measured positively in the counterclockwise direction from the x-axis. So here I want to talk about 2D motion on a level. That is to say, we're not shooting something off a cliff and having it fall. We're shooting it at some altitude and it's landing at that same altitude. So it's level 2D motion. And by the way, one of the questions often asked is, when you have a trajectory motion, what is the velocity at the top of the trajectory? And a lot of students want to say it's 0 because the object is going up, stopping, and coming down. But don't forget, it's also moving forward at a constant rate the entire time. So at the very top, the speed will be whatever the x velocity is, and that will remain constant. Here, the velocity is made up of two components. The velocity is 100 at an angle of theta, which I put at 30 degrees because we know the sine and cosine of 30 degrees. The sine of 30 degrees is a half. I don't think I wrote that anywhere. And the cosine is the square root of 3 over 2. So the sine of 30 is a half, and the cosine of 30, so we can write it here, is the square root of 3 divided by 2, which is about 0.87. Remember, square root of 3 is 1.73. It's about 7/4. So if you have to do a calculation, 7/4 is a good estimate of what's 1.73, the square root of 3. When we divide by 2, we get like 0.866. So I've kind of rounded that off because remember, to get the x and y components, this 100 doesn't do us any good because it's not in the direction of motion. The motion is in this direction and in this direction, superimposed. So the velocity in the x direction is v cosine. Remember, cosine comes before x and sine comes before y in the alphabet. And that is to say, c comes before s and x comes before y. So the y velocity is v 100 sine theta, which is 50 meters per second, and the x velocity is v cosine 87. I'm interested in finding the range. How far will this projectile go from where it was launched to where it lands? So let's talk about it. We could realize that there's symmetry in this launching. That is to say, what goes up must come down. So what I've labeled as Roman numeral 1 is the same as the motion in Roman numeral 2, but it's reversed. It's going up here and coming down here. It starts at 100. It comes to the top with a Vy of 0. It still has an 87 meter per second forward velocity in the x direction, and it lands as the mirror image of this at 100 meters per second. And units are important, so we write them in. So let's look at the big four, which we often write down. If we don't know where to start, we write down the 4 equations of motion, and we say that we know the initial velocity down here, it's upward at 50 meters per second. At the top, the up and down velocity is 0, so I know V0, I know V final, and I know that the acceleration is downward at 10 meters per second squared. That's G. It acts in the downward direction, so down is negative because I'm calling the upward velocity positive. So if this is the positive direction, gravity acts in the negative direction. Signs are important. Not these signs, SIG and S signs. So here are the three things I know. V final, V initial 50, V final 0 in the Y direction, and the acceleration negative 10 meters per second. I happen to know that this equation will be very useful because I can find the time to the top. V final is 0. V initial is 50 in the Y direction, I'm talking, and minus, because acceleration is negative 10, times time. So 0 equals 50 minus 10t. Move the 50 to the other side, divide both sides by negative 10. The time going up is 5 seconds. So the time coming down, by symmetry, is 5 seconds. The flight time is 10 seconds. To figure out what the range was, we multiply the 10 seconds. We use distance equals rate times time. The rate is 87, the time is 10, 870 meters is the range. So, by the way, I was interested in finding what the maximum height was above the ground. Now that I know the time, I can use a couple of different equations. I can use the one that has the quadratic in it and say negative 1/2 g, which is negative 5 times 5 squared, half the time, just to this point. So that's 25 plus initial velocity times time. That's 250, and negative 125 makes the maximum height 125 meters. Or I could use the average rate, which is 50 and 0 over 2, which is 25 times t, which is 5. So 25 times 5 is, again, 125. I'm going to get the same answer, of course, no matter which of the big four I use. That's a typical level trajectory going up. Now, I'm suggesting something different. If you're looking for the range, and only the range, that's a relatively long way to do it. If you memorize one equation for the range, which works on level launching and landing, you will get the answer a lot faster. And remember, we want to be able to run through these problems in less than a minute apiece. 75 questions, an hour. So you want to be able to do things in under 60 seconds per problem. If you do that and get 82% of them right, you're going to get an 800. And that's what I say, it's very possible to do that. So let's talk about how to find the range equation for this so that if they only ask us about the range, we can get the answer in about 15 seconds. That's coming up next here as part of your kinematic lesson plan for 2D motion.